Swayam Prabha. Digital India. Educated India.
This is lecture number 31. In this lecture, we will be talking about reinforced soil retaining walls. In fact, this is one of the biggest contributions of reinforced soil, because of which you are able to construct many retaining walls made of this reinforced soil. This has significantly contributed to infrastructure construction. The way that the reinforced soil evolved, we have already seen, and its applications to reinforced soil walls or the retaining walls is something that's very unique. And in fact, this is the one that we had in a classical retaining walls, in which say for example, you call the gravity retaining walls, in which the weight of the soil exerts some sort of lateral pressure component, and you, by the weight of the soil alone, the retaining structure, you try to resist the horizontal force. So that is a concept of a gravity wall, in which the weight of the retaining system and its you try to have some geometrical proportions in such a way that it will withstand all the pressures, both lateral pressures and the vertical components of pressures. So we design this, and in fact, sometimes when it is required, we try to provide shear keys also to increase the shear resistance, because when there is a lateral force acting, there should be some sort of resistance that needs to be provided. Either it can be a shear keys here, and it can be even at the bottom sometimes, like, so that is one concept for gravity retaining walls. Next thing is reinforced concrete types, in which you have, when bending and bending develops, so you try to put some sort of, this is a reinforced concrete wall, in which because of you try to understand the bending moments developed, and try to provide the steel to withstand the bending and all that, and try to have a suitable design methodology for that, which is well established. So you have essentially you try to resist the earth pressures by this cantilever action here, and we also have what you call the buttress and counterfort retaining wall, in which you try to provide, when you want to reduce the thicknesses, the thing is that what happens is that the base width of this wall, and there are certain proportions in our retaining wall literature, in which you must have some sort of dimensions here, some dimensions here, some dimensions here, and then when the height is beyond 7 meters or 8 meters, the possibility is that these widths become little bigger. So we try to provide some sort of counterforts here, which will see that the concrete areas are reduced, the quantities of concrete are reduced in this system. The other one that we have in retaining walls is that you try to compartmentalize the systems, like in the form of a bin, or you try to, this is a system in which you can place all these materials, and it's like it acts as like a confined material. In a confined material, that though there is a pressure from all the sides, this confinement that we have, it takes care of the pressures developed. So that way, it's a simple system that we have. In fact, this has been used very effectively in some of the flyovers in Bangalore, which is very cost effective. And the final one was that what we will be talking today is the reinforced earth walls, in which you have a facing element, you have a geosynthetic reinforcement, and you have a backfill. So this we call it, there are two types here. One is actually mechanically stabilized earth walls, we call it MSC, with metal reinforcement. One can have metal reinforcement, otherwise you can also have geogrid reinforcement or a geosynthetic reinforcement or whatever. So these are the categories, and this is a way that it looks like, that you have a reinforced soil, and then you have retaining wall or a foundation soil, and you have different elements here. You have a segment, this is all called, actually this type of wall is called segmental retaining wall, in which you have a this called segmental facing. We'll see that what is the difference. You can have a there are different types of facing. One can have, as you just mentioned earlier, this retaining the reinforced elements are designed to take care of the lateral pressures. Once you know what should be the length and the spacing of that, we have seen this idea in the reinforced soil slopes, and once you know this design comfortably, then whatever you get here, the pressures are somewhat going to be minimum, and we try to provide some sort of segmental facing types. It can be full facing or it can be even concrete panels, that what we see in most of the flyover projects in India. And we also have what we call a shear key or a mechanical connector between the two facing elements, and then this is a geocentric reinforcement, and you have a geotextile drain here, and you have a granular leveling pad and all that. So, this is a simple way of reinforced at retaining wall system. We will see its design and how it can be constructed in the field and all that in this lecture and the coming lecture also. As I just mentioned, Vidal is one person who developed this technique, and when he developed this technique, he had this precast concrete panels. Then this is a backfill. This is actually backfill. This we call it a wall fill. Wall fill means this is a reinforced soil wall. So, whatever you are trying to use it as a wall fill, because it should have good friction, right? Good friction should be there, and that is what we call it the reinforced earth. In fact, the same company has been continuing and then constructed a lot of reinforced earth walls in abroad and in India, and it has been quite very useful technique. And you can have steel strips as a reinforcement, you can have geotextile materials, you can have the conventional geotextiles can be it can be non-ovens, ovens, knitted, stretch bonded, many types of materials that we saw earlier can be used as a reinforcement material. Sometimes even geotextiles, special geotextiles like say for example geocomposites, like as I said, when the pore pressures are going to be higher or if the clay is somewhat poor quality, we can use a geocomposite in which you have a reinforcement as well as a drainage material attached to it. So, the reinforcement is good enough to take care of the lateral pressures, and the drainage action of the geocomposite helps in draining the backfill. What are the principal requirements of the reinforcement? We have seen that strength of the reinforcement, in fact, we did calculations on slope stability and other things. Strength of the geotextile or the geogrid is important, and its stability, like it should not creep too much. Of course, the polymeric materials do creep, and this strength and stability are important. Then durability, like how long, because you are trying to design for 100 years or 50 years or whatever. Then ease of handling, reinforcement should be able to, you should be able to handle in a very easy manner, like you can bring them to in a lorry or in some sort of containers and put them on the field. Very importantly, high coefficient of friction or the adherence with the soil, like we need good friction between the soil and reinforcement. That's very important, because that's a whole concept of reinforced soil. Now, it should have low cost also, like why are you using this? You need to have apart from technical advantages, like we said that we can increase the width of this reinforced concrete, the thickness of the stem and all that in the case of reinforced concrete retaining walls, you can say that, but we essentially want low cost, ready availability. Ready availability is something very important. Why? Because it should be done faster, it should be comfortable in the way that it can influence the whole system. So, the whole construction should be faster, so we saw that advantage of the reinforced soil earlier. It should be able to contribute, it should have some of these principal requirements, and see that it serves the intended function. So, it should have among them the important properties, as I just mentioned, tensile strength, like say for example, there is so much earth pressure that is developed, with some spacing and length of the reinforcement, we get this tensile strength, like that is one thing. We will see that tensile modulus is very important, because if there is a deformation, movement is very important, and reinforced soil walls also deform, and the modulus of deformation, like when you get what you get from tensile strength is very important. And the third one is interface shear strength, is also very important. These three components are very important in the design. So, how do you go about design, particularly when you are trying to use the the reinforced soil technique in this is something that we use a limit equilibrium approach. We need to look for stability, external stability, internal stability, and the properties of the backfill will be the friction angle at constant volumes phi and c. These shear strength parameters should be obtained corresponding to large strains. This is what we saw in reinforced slopes also, that we try to conduct say direct shear test or a triaxial test, say for example better triaxial test in which you get c and phi parameters for effective stress parameters, and for say for example 3 or 4 normal stresses, and then you get c phi from these large strains. Essentially CV means constant volume strains, and design strength of the geogrids is what we have seen that the company gives some property. Say for example, we have seen one example where you can say it's 50 kilonewton per meter, and then you have various factors like the partial factors like FM, the manufacturing constant, environmental factor, damage factor, and all that. Okay, all these factors are there, one can use, and then finally you should just use this as a design strength. Okay. So what are the external stability considerations? These are all standard even for regular retaining walls. We know that we need to design the retaining walls for bearing, overturning and sliding and deep stability. Like the retaining wall, whether it is a reinforced earth wall or any other like conventional retaining wall, it should not slide, right? That is one thing. So sliding resistance is important, overturning is also important, then bearing capacity failure should not occur. Say for example, it has some, it will once you construct a structure like this, since there is nothing here, there is some sort of pressures and moments that get developed, and the pressure, bearing pressure should be satisfactory here. Deep seated stability, like you may construct a retaining wall, but it should not be in a slip circle. If this is you should construct you should really do some sort of analysis in which wherever you are going to place a reinforced earth wall, the area should not lead to some stability like issue like this, global stability we call it. So all these things have to be satisfied. In fact, to design the reinforced earth walls, we have two methods. One is called tie back wedge method. I will just explain what it is. And say tie means a tension member, and then this is a wedge that is forming, right? So you try to put a reinforcement like a tie member and then keep the wedge back in position. So that is why we call it tie back wedge method. And the assumptions, some of the things are that, like you have a rotation is about this thing, and the earth pressure distribution is like this. It's like 45 minus 5 by 2 is a active failure zone. Like this is the failure zone at which the failure surface, and this essentially we assume that the wall is cohesionless and it rotates about this, and the earth pressure variation, we assume that it's the same everywhere. Like we assume active earth pressure conditions. Okay, active earth pressure conditions we assume, and because there are two conditions, state of in the beginning I said the state of soil, is it a K naught condition or a K condition? Like is it the coefficient of earth pressure at rest is there, or is it for the active earth pressure we should design, is something very important. So this material, like you put a geotextile, say for example what you are trying to do is that we later will put some geotextiles here, and then there will be some deformation, so because of which there will be an active condition. So we assume that the variation earth pressure is constant, and the earth pressure lateral earth pressure diagram will be like this. Earth pressure diagram in terms of this thing. This is just a Ka constant. This is Ka gamma h, right? Ka gamma h is the pressure, and now you have a surcharge also Ws. So plus you add. So this is actually the earth pressure at any point due to its its variation with depth as well as due to the surcharge as well. This is called tie back wedge method. You have another method which is something which people have based on observations of many of the RE walls, they have observed that you can earth pressure, if you really measure, it will not be, an active condition, it will be in a K naught condition for some about at least 5 to 6 meters, and based on that, in fact, say they say that in fact K naught, they just put here, you can see K naught into that is one thing. K naught will be, it's about 6 meters up to, say for example, if you are trying to measure small height retaining walls like 3 meters or 4 meters, if you measure at pressure, it will be K naught, like I have measured. In fact, in one of the cases in Delhi, it's about 7 or 8 meters, but I was measuring with depth at some points. The earth pressure was K naught. We have a measurement of by using some diaphragm and all that. There is a method of measuring earth pressures. I used it and found that the earth pressure is corresponding to K naught condition, like, which means that soil has not moved, like there is no lateral strain is 0. That's what the point is. So when you have that, so K naught is always 1 minus sin phi, and Ka is 1 minus sin phi by 1 plus sin phi. So as the height is increased, it will become K naught to Ka, it will decrease actually. Okay. Say for example, if the wall height is 8 meters, so it will be this. So you have to assume a distribution diagram like this. Okay. Earth pressure distribution diagram like this, and the same thing also here, like there the difference is only that you have the other one superimposed on this. So this is the coherent gravity method is, what it means is that people have observed that many of the retaining walls of particularly smaller heights are having a state of rest, and then the even the failure diagram, in fact people have measured. How do you measure the earth pressure diagram? In fact, you can monitor the tensile strains in the reinforcement. Instead of the 45 minus 5 by 2 that what we have seen, this is the earth pressure, the failure zone that they have taken. In fact, even if you just do a finite element analysis, it comes like this. It is this point, like in the previous case, it is like this, So whereas you are just cutting it here only, what it means is that now the advantage is that earth pressure that you have to consider in design is much less in the coherent gravity method compared to this case. Here you are trying to consider all this pressure, whereas in this case the earth pressure is only like this, which means that this method is somewhat economical, is it not? You are trying to make this, if you make based on the observations, this is a method that was developed by some group of people in France, and particularly it is valid for steel reinforcement, because they are initially working for steel reinforcement, and steel reinforcement is stiffer. We have seen that. And whereas a geotextile is a flexible reinforcement, it needs some strain. So I can't assume this sort of distribution. I should only go for the previous distribution. In this distribution, what people have observed is that this is just so it also rotates about this point. Not in the other case, it was somewhat reverse. Like you can see in the previous case, the rotation is about the toe, whereas here the rotation is at the top. So that's what the assumption that they have, and they have measured, actually they have measured the earth pressures, and then even measured the strains. Like you can place you can measure the strain along the reinforcement, entire length of the reinforcement, and in this zone what happens is that if this is the lateral force acting, the tensile strains direction will be in the opposite direction. Okay, the strain measurements, they will be like this, and beyond the failure point, they try to hold it. Okay, the direction of strains would be different on both sides. So based on that, actually shear stress distribution along this reinforcement, because this is a shear stress mobilization, right? Shear stress mobilization along the reinforcement. Based on that, you can locate this actual failure surface, because at this point, beyond this point will constitute one location where the shear strain that distribution will be different on either side. So that's what the thing is, that what it means is that you can construct this like what people have done is using finite element analysis also, or using experiments also, people have measured using centrifugal, you can put reinforcement and measure its tensile strengths. So, at this point, actually the point at which it is maximum, we have seen one even in the Binkwitli method also, they assume some maximum strain distribution, and we made some assumptions there. Similar to that, we have the location of strains here, so it will be like that, right. So, you construct this particular line, and based on their observations, they observed that for a h by 2 distance, it is about tan inverse 0.6, and another h by 2, the height of that, it will be straight line, and this particular thing is 0.3 h. So, actually this is the line of maximum tension reinforcement. So, if you observe for all the reinforcement elements, where is the maximum tension, and then locate them and join them, actually that there is you can find out the distribution of tension on the reinforcement. So, as friction develops along this, there will be a strain mobilization, and then all these points you can join, even in the FLAC or Flaxus analysis you can get that. So, this is one important method that one should understand. So, these two are some design philosophies that people have, and another important thing that is that, okay, you have seen that there are three different ways of assessing the external stability. We just saw the pictorially the diagram, and how do you really calculate that? We will see that. So, for example, this is the earth pressure diagram that we have to consider, like half KAB gamma h square, half KAB like 0.5 gamma Ka active, because this is for a geotextile, okay, and what I am telling is a geotextile. So, half Ka gamma h square, and then this is h by 3 we assume, and then this is the other one is Ws is what other one. So, you have to like the other important thing is that for the bearing pressure, we assume that there are two types of earth pressure distribution, the distributions of pressure, contact pressure actually. That we have a trapezoidal footing, trapezoidal distribution, where you have a maximum tension developed and then the minimum tension developed, and we have that B by 6 rule, right? B by 6 rule we have. So, that B by 6 rule is very important, and here also similar thing we measure, and that is called trapezoidal distribution. That is valid for stiff footings, rigid footings like concrete footings and all that, and whereas this is, since reinforced soil is a flexible structure, and you will not have the development of maximum pressure and minimum pressure, it gets adjusted in such a manner that if L is the length of the foundation, like an RE wall length is about L, over a distance L minus 2E, it gets adjusted, okay, sigma B is what you get, and so instead of a trapezoidal, you can have, trapezoidal is one type of distribution you can assume, and this is called Meyerhof distribution, okay. In trapezoidal distribution, we assume that you have a maximum value, you have a minimum value, and the distribution varies in the form of the trapezoid. But then that is valid in the case of rigid foundations, but reinforced soil being a flexible structure, what happens is that any pressure gets redistributed, and you will have only constant value. So, that is the maximum value sigma V you get, and this is okay, this is a usual thing. So, this is another important thing, it is called Meyerhof distribution. So, how do you get this factors of safety? Like we have seen that for sliding, there is a sliding force which is because of KAB gamma h square by 2 and the surcharge and all that you just put here. Resisting force is nothing but the weight of that 2 at the bottom comes here. So, 2 into mu is nothing but the mu is nothing but the coefficient of friction on the base soil of the reinforced soil, and it is the total resisting force, gamma W into height plus WS is a total resisting force, right. So, the factor of, so you try to calculate this, and the factor of safety has to be 2, right. This is one thing. Now, even for the overturning, you have to calculate resisting moment and also the overturning moments. So, this is actually, you should know the base of that, like 1/3 where it sacks and all that, and then these are all expressions. Actually, details are, you can simply derive these equations which are straightforward considering the equilibrium of forces, and the factor of safety should be somewhat says 2 or something, and most of the cases it is a sliding that governs the design. So, in this case overturning is not a serious issue. If you are able to satisfy the stability issue, the sliding stability issue, automatically this gets sorted out. Then bearing pressure. Bearing pressure is that, I just showed you about, I told you about the two types of distribution. One is called trapezoidal distribution. You can do that also, and also you can do Meyerhof distribution, which is nothing but like there is a simple expression that one can get based on the moments and the forces acting on the at that below the foundation. You will get a simple expression. One can derive this considering the weights and all that, and at pressure coefficients. The maximum pressure will be this, and from Meyerhof distribution. Even you can get from trapezoidal distribution also. We know how to get maximum pressure and minimum pressure. So, actually that this pressure, whatever pressure, should be less than the bearing pressure of the soil. That is what is very important. Whatever is the pressure that is created because of the this pressure should be less than the bearing capacity of the soil. So, usually an allowable bearing pressure of half the ultimate is taken, ultimate pressure is taken. So, we normally have a factor of safety of 2. Normally, you can see that bearing capacity calculations we know, and we calculate, say for example, 200 kPa is the bearing pressure of the soil, and if this pressure is say 150, it is all right, like that, right. Then we also say, as I said, we are looking at all these global stability issues. We should look for, you may construct a retaining wall, but it should not be located in a slip surface. So, all potential slip surfaces should be investigated, and a target factor of safety 1.5 is used in this case. That is what you saw was external stability. Then what is internal stability? Like now you have introduced a reinforcement. So, it should not fail by tension, or it should not come by pull out. It should not just come out like a pull out, or it should not fail by tension. Like there is a tension failure where there is a clear breakage, where this pull out, reinforcement just comes out, this pull out. For that, we have a method. How do you calculate this tension failure and all that? You will see that this is a diagram, there is a surcharge acting, and you take a particular reinforcement that is located at a distance hi, and this is what I said is actually the Meyerhof distribution type. The pressure, actually the foundation pressure acts here, right. You can assume that the same pressure acts, this is for the maximum height. If the height of the wall is h, and this is the maximum pressure that acts here, and then as we go up, the pressure comes down. So, this, at any level hi, you can always calculate the vertical pressure acting, total vertical pressure, and for that you are actually calculating horizontal force. You put Ka times vertical pressure, you will get the lateral pressure, and then design for Ti. What we say is that at this Vi, Vi is a horizontal space. We assume that at this ith level, which is at a distance from the top hi, and Vi is a spacing, the reinforcement is effective. It can take care of it can provide force within that spacing, right. So, how do you calculate that reinforcement force? It is actually sigma Vi you calculate, and sigma 1, then Ka times the sigma V, we will get that we will see that, okay. So, the grids carry tension as a result of the self weight of the fill and the surcharge acting on the top of the block. That's what we did. Like this is what I said, this is actually, if you have seen the previous figure, yeah, we have seen the expression for, this is nothing but the vertical pressure into Ka times, okay. And actually, if the soil has cohesion, we introduce cohesion term also, otherwise it is not required, and this acts over a distance Vi, okay. T is nothing but, it is like Ka times into this vertical pressure minus this actually whatever is this thing, and then into Vi. As I said, it acts over a distance Vi. The Ti is nothing but it acts over this distance, this area which is with the spacing Vi. Okay, how we have this equation. So what we do is that we calculate for different reinforcement types, like I will just show you that. Yeah, this is an expression, and we'll see the different you will have as a higher as you can calculate this as you go down, the spacing has to be little higher, and depending on the type of reinforcement you can develop this sort of curves, like as I said. So this is the Vi spacing. You can have different Vi's, and also the depth. Actually Hi is here. Okay, Hi is everything is known here, and once based on this you can calculate the Ti required, or otherwise we know what type of reinforcement materials I have. I have, say for example in this case 55 grade and 80 grade. I can construct back what should be the spacing if I have this sort of reinforcement at different depths, is what is given by this equation. So this is that, say for example 40 grade I don't want to use, but I can say that 40 divided by all the partial factors, right? So maybe you will get some 20 number or 15 number here. 15 is equal to this, and then you have the only variable, you assume this as c equal to 0. So this term vanishes and all the terms are known, and only unknown is, so you put different values of Vi, right? It can be from 1 meter to 0.5 meters to 0.3 meters and all that. You will get a diagram like this, 0.3, 0.4, 0.5 like this, and then you can get a diagram like this. So it is called spacing versus depth diagram, and this will help us to, we'll see how it helps us in calculating a spacing. Okay, that's one thing. We know how to calculate now. Some, the reinforcement, and particularly in the case of geogrid, say for example some grade of geogrid is available, how to work back what should be the spacing that needs to be provided, so that spacing, in that spacing the lateral pressure is really handled properly or taken care of. Then once you provide this reinforcement, we have some more considerations, like it should not fail. So we have to calculate tension using the wedge pull-out failure also. Consider the possibility of failure planes passing through the wall and forming unstable wedges. We try to have a number of wedges like this, and what we do is that, say for example in this case, you have in this wedge of this particular thing, you have 1, 2, 3, 4, 5, 6 layers of reinforcement here, like 1. So you have 6 layers of reinforcement, and that they have to be in the position that wedge should be stable, which means that the sum of all these tension forces in the reinforcement should be such that it is stable. Like the T should be equal to the it's a component of this weight, okay, which you can get from, in fact I will show you that it can be from graphics element that we know the basics of graphics, engineering graphics. One can get that from what is called polygon, force polygon, you can get that. Okay, I will see that, like if you know the weight acting, the horizontal, actually this is a horizontal force acting. Imagine that there is a curvature and there is a vehicle goes like this, there is a component of F1 that is acting, there is a vertical load acting. So it's like a retaining wall and a flyover, imagine that. Okay, so what we should, so we are trying to take a wedge here with an angle beta, and then there is a, because of the weights acting W and all that, there is a resultant is a force, resultant, you have a resultant which has an angle phi W with this, and then you have a theta tension force T which will be required to keep all these things in equilibrium. That is what we try to find out. What we do is that we will make some assumptions. Each wedge behaves as a rigid body, friction between the facing and the fills is ignored. We investigate a series of wedges as shown below, like we take a number of wedge failure considerations here, like say even very important is that, say for example you have so much reinforcements, 1, 2, 3, 4, 5, 6, 7, 8, you have all 1, 2, they are all reinforced. So, in this wedge, if I are trying to look at this wedge stability, I should see that there should be the tensile force should be so much that this wedge should be in under stable conditions. That is what we will investigate in a series of wedges. This is what we do. I said the force polygon, right? You can see here, and these are all the forces that can act. And for a simple case of only surcharge acting, and you can simple expression can be derived. This is just based on force polygon. One can calculate this expression. Imagine that resolving into vertical forces and horizontal forces in the direction of appropriately, you can do that. So, for simple at any level, by changing beta, what we do is that we investigate this T max for different betas, like as I just showed in my previous diagram. Betas can be vary from, there are so many betas here, then there could be many betas here. So, all that betas we investigate. It is a simple simple Excel program one can write to have all this information and then plot like this, okay. And then once you plot that, you will have the maximum value. So, you take the maximum value as the tensile force required to keep all the wedges in equilibrium. That is what is required. It is a very simple case where you try to calculate the maximum tensile force required to keep all the wedge, so that the wedge failure will not occur. That is a principle here. Like all these wedges are all contained, put in this form, right? Okay. So, in fact, for a simple case where there is only a surcharge, one can, it is a simple equation you will get. T is nothing but h tan beta into gamma h, and if h is the maximum, say for example, height of the returning wall is 7 meters, I put 7 meters here, and surcharge I know. Surcharge is nothing but, say for example, 20 kPa as per IRC, or 22 kPa or whatever. So, you can put that number, you will get the maximum tensile force required in the is actually total reinforcement force required. We will see that, okay. So, now the other important thing is that the wedge pull out failure, it is also a function of the overburden, right. The thing is that this is all that overburden pressure, and whatever is that, there should be sufficient length beyond the failure zone. Actually, if this is a failure surface that we assume, and there should be enough length to see that the tensile failure, we have seen factor of safety, the tensile force we calculate, and the pull out resistance also we calculate. There should be adequate factor of safety there. Otherwise, the pull out resistance should be higher than the tensile force mobilized, maybe 2 times. Okay. This is another one that one can have, so what is the anchorage force you can develop, you will get is also given by, actually that length that you have, the length, this is called the anchorage length, that length at any point one can calculate, and that is given by this expression, and the anchorage force or the pull out resistance. Well, there are 2 terms, one is called a tensile resistance, tensile force mobilized in the reinforcement. Now, you have to calculate the anchorage force. Anchorage force means pull out resistance. So, that is nothing but it is a function of the length of the reinforcement beyond the failure zone, and also there is a coefficient alpha, then tan phi w, and depends on the surcharge also. For each layer of the reinforcement cut by the wedge, the lower of the design values T design or the TA is used to determine the contribution from reinforcement. So, what we do is that we calculate whichever is lower, and then we try to then again compare the mobilizing force to the resisting force. We have to see that we make all these calculations of say what I said earlier, previous section was that you calculate the, this is in terms of the again the wedge failure stability, and there are this is in terms of the anchorage, okay, and the previous case was in terms of the tension, okay. So, what we try to see is that all the forces we try to compare and see that the sum of all the forces should be more than or equal to the total tension mobilized. the total tension is nothing but the total tensile force required for the wet stability, right. So, this is we will see that in an example, that you will get much more clarity on that, and this is a typical case of a GRS wall constructed with a face like precast concrete facing, and you have a wrapped geotextile also one can have, there are many types of facings are possible. So, there are a number of design methods. In fact, as I said, GRS walls have been very useful and they have been very cost effective, and so there are design approaches that are developed, and essentially there are two design methods that we follow. Actually, Rankine approach is one thing, like 1 minus n phi, that type of approach we use, and we have a Federal Highway approach, which is by one standard code. Then we have NCMA approach, another one, and we also have BS 8006 UK code. These are all from US actually, and then you have a US code BS 8006 is another standard code, and most of the codes in the world, they follow many of these codes, and then sometimes they follow in different countries, they have their own codes also. So, before I go further, I want to illustrate a few more points here, that as I said, facing can be anything. So, people have tried different facing blocks, because these are all very simple actually, that one can carry it with hand. Like if you are familiar with some wall structures that are constructed, in the concrete panel that we have, it needs a lot of cranes and all that, here you don't need cranes, you just have a simple equipment, and also the simple company that manufactures this type of facing blocks. It's called segmental retaining wall units. Like they are quite useful, like these are all facing blocks. You can see that you can construct like this simple facing. Like this is a typical example that we have seen in many places in India, some places at least. This is a facing, it's called segmental wall design. This is another type. So, the advantage is that it's easy to construct, you can have a nice finish, and it is also cheaper. That's one thing, because the overheads, because of the heavy equipment are not there. There is another type, you can say simply blocks only are kept compared to a panel of 1.2 or 3 meters. The panel will be 1 meter to 1.2 meters. It depends. So this is also another one. This is another one. You can just see many types of structures one can have. So the way that we construct is that it's like these are all simple blocks. They can be handled, and this way it is shear key, as just mentioned. And this is another one, the type of thing we have. So this is how it is done. Okay. So very importantly, actually there is a since you are putting fascia blocks, one should understand that they can fail also. Like it's not easy to simply stack one over the other. So like similar to regular retaining walls, you should do for base sliding, overturning, and bearing capacity calculations, internal stability calculations, pull out, tensile resistance, internal sliding, particularly like this. I have seen a couple of failures like this, because we think that simple construction is easy, but it's not easy. Then facing, there could be a connection failures, there could be column, it fails as a column here, it does, there is no then there could be some toppling failures, many things are possible. So though the facing looks very impressive, one should be very careful, because one should look at all these possibilities. So this is what I just mentioned, like it can fail and all that. This is another type failure. So this is a column shear failure, toppling. We have seen many cases in India actually, because what they do, okay, this is all simple precast block, so I can get from fly ash. They try to do a poor quality, then the possibility is that it can lead to failure. Okay. So this is a simple example of global stability. Like you have to investigate. Maybe this is a nice. Say for example, this is a typical what is called segmental wall, what is called modular concrete blocks, you can have it. This is a reinforcement layers, okay, and you have a drainage here, drainage pipe is here, and geogrids are placed, and this is how it is there, right. I just want, then you have to investigate the because it is forming this part of the slope, right. So, you have to investigate all the failure surfaces. You can see that 1.33, 1. You have all these numbers. Definitely, it's more than 1.3. So, it's okay like that. So, you have to do some sort of analysis like this. So, the typical factors that we recommend are, it could be like this, base sliding 1.5, bearing capacity, tensile overstress, all that you have to verify, toppling, and one should calculate and do that. Global stability 1.3 to 1.5. In the previous case, it's more than 1.3, so it's okay. So, the construction details, yes, this one way, this other way, like this is a drainage element actually, This is another blocking and locking bar. This is a general view of the wall construction. Placing blocks, see you have a thread here running. Wall ties, fixing false facing. You can have false facing also. This may be actually required facing, this can be a nice facing, whichever you want, okay. Like people have false roofing. Locking geogrid between blocks, this is one type. So, sometimes safety barriers on the walls at the top of the wall also should be done, because once you construct the wall, people should not just it should not lead to any problems. So, this is like that. So, many one can have a nice fencing, and many things are possible, like examples of finished structures. This is another one. This is a nice treatment that one can give. Yeah. This is, I just want to show you the influence of because of the earthquake, the possibility is that one of the railway lines in Japan has yielded, and that was reconstructed later with Ardewall technique, okay. And geogrid reinforced soil wall along the JR, Japanese railway Kobe line. Kobe line is an earthquake that occurred, and the thing is that it's before the earthquake occurred. And you can see the same photo after the earthquake occurred. So you can see that there is a collapse of all the structures, but Ardewall is still stable. Okay. So this is another one. Damaged masonry wall reconstructed to GRS with a full height facing. This is one masonry wall type of construction that again it got failed in the earthquake, but they reconstructed with full height facing. I told full height facing. It means the facing is fully there. In fact, we did one is full height facing is also possible, like a simple facing, fully put one member. No, don't worry about simple blocks like that, right. Another example of poor quality in Bangalore. This is one case where it was not well done. You can see that. So this technique is quite simple. I would like to just now illustrate with you with a simple example. This is where I would like to end. We have an 8-meter high wall to be built using the sand fill and the polymer reinforcement. The sand has a friction angle 30 degrees, bulk density is 18 meters, and surcharge load of 15 kPa is there, and the bearing capacity is about 300 kPa. You have two geogrids available, grid A 20 kN per meter and B equal to 40 kN per meter. Both have a bond coefficient of 0.9. Okay, these are all known. And then the fill has 250 centimeters of compaction lips. Why this is required is that you compact the sample and put a geogrid. So next one should not be, it should be in multiples of 250 only. Any placement should be in terms of 250 only, because the thickness is important here. And the location of the geogrids, you have to redesign. Say for example, you have a even your facing block, if you are using a modular blocks, it would be 250 mm. Then put the all heights. This is a very important parameter. If you decide this, then spacing, design of your facing blocks all depend on that. Okay. As I just mentioned, this is all the once you know the quantities and factor of safety, I gave an expression for the sliding stability. Like if you use a previous formula that we discussed, to avoid sliding stability, the factor of safety of minimum is 2. So, use that number and all the quantities like KAB, height and surcharge, everything is known. You substitute back in the equation, the minimum length required is about 5.83 meters. So, you can take 6 meters. The height of the wall is 8 meters and 6 by 8 is 75%. So, 0.75 is the length of the 0.75 L is the length of the reinforcement. Okay. Actually, this is very important, so sliding stability is taken care. Similarly, you can do the overturning stability, like you can put all these numbers. It is actually given in my book also, this particular examples. And the factor of safety with respect to overturning is, if you just put all the numbers, it's 4.26, okay, more than 2. Now, using trapezoidal distribution, you calculate, I said you can do Meyerhof distribution or even trapezoidal distribution and use, for example, in this case, I would like to show the use of trapezoidal distribution. One can see that, and you get maximum vertical stress as 271 kPa, which is less than the bearing capacity of the soil. And minimum values 159, maximum minimum values, it's more than 0, which means that there is no tension developed. Actually, if you are using, why use this trapezoidal distribution is that we would like to satisfy the no tension criteria also, but remember the reinforced soil is foundation is a flexible structure. So, we better use a Meyerhof distribution that leads to, actually if you use a Meyerhof distribution, this value will be much lower. So, we will be, instead of telling that it's 271 is less than 300 kPa, this value will be much lesser, because there is a readjustment and this sigma V minimum will be 0. It will also come down because there is a readjustment. Now, as I just mentioned, how to calculate the tensile forces, right? This is that horizontal force into SV is the spacing, right? And this is, say, for example, you assume a spacing of SV, and this is a horizontal force, this is a tensile force required to keep that place in position. Ka, this is what this thing, and sigma V is nothing but this formula is there, right? So, you substitute all the quantities and then put in terms of the SV, like see the Ti is nothing but the design strength values, like I just have 2 geogrid materials and their design strengths I know, like 20 and 40, like in the previous example, in the statement of the problem I just mentioned. 2 grids of different design strengths are available, grid at 40 and 20 and 40, okay. This 0.9 are available, this we should remember, okay. So, you put it here using the, say you are putting it here, that number, and then try to just put this sort of equation, and you will get a grid like this, grid A, grid B. You just get, depending on the spacing and all that, you will get some sort of simple diagram like this. And actually, we are only going for close spacings only. What it means is that if you are using a geogrid of A, which is somewhat weaker compared to this, 40 kilometers is bigger, right, stronger. So, you can have 0.25 spacing, right, up to then up to a depth of about this much length. So, here grid A, 20 kilometer per meter, you can just, it starts with you have to go for lesser than, which is not possible here. So, what it means is that grid A you cannot use at the bottom because it's less than 0.25, it is going here. So, I can start using this 0.25 only from here at 6 between 5 and 6, so say 5.5, that's what it means, okay. So, once you do this, then this helps in that fashion. So, one can construct a 0.5, just put in a simple Excel program and then get this thing and plot like this, you will get that information. But essentially, we are going for this case, and wedge stability check also can be done. and we can trial wedges can be done and calculate the total required force. This is one thing I just mentioned, and you have to calculate checks with and without surcharge, and as just mentioned, there is an equation for a critical angle that you have, and this is an expression that we have, and for any reinforcing related depth jet below the top of the wall, the pull out resistance is given by this number. So this is behind the retaining wall, behind the failure zone, or the in the anchorage length we call it. You calculate the passive resistance. So you get all this information, and what we do is that we try to make all these calculations, and say for example, this is a diagram that I would like to show here. Wedge depth, you have wedges at different depths 1, 2, 3, 4, 5, 6, 7, 8 meters, and force to be resisted, total force that you have to resist will be if it is 0 surcharge is 8, and if its surcharge is 3. So you calculate all these numbers. This is all the force to be resisted by the members. Then the geogrids, like I just mentioned, you have to just put some numbers here, in the sense that so if I have two geogrids, we have A and B, and you have A geogrid is 20 kilonewtons, so I put 2, 40, and this is one number. And pull out resistance is, we have an equation that I just mentioned. Pull out resistance you are getting, with and without surcharge you calculate. Without surcharge, pull out resistance is 42, with surcharge is this, and whatever is minimum, say for example, you have to take here, right, and then see that whatever is available, okay. See that you have to compare, both of them you have to compare. Available force, minimum of PD and PP, okay, 40, okay. So here it's 80, okay. So all these things we maintain, and see that this is now, this is the minimum, this is what is we have, and the design strength you compare actually, okay. So they have to be more than that, any stage, like pull out resistance have to be higher. This pull out resistance have to be higher. Say for example, at 0 WS equal to 0, say this is 5639 is a pull out resistance available, the design tensile force is 700. So that's what we see, that all the time the design requirement is satisfied here in terms of the tensile forces and the force to be resisted. Say for example, here 192 you can get from this combination only, 15 into 20 plus 10 into B, 10 B is 40. So that comes to totally 700, and that 700 will be higher than this, this is higher. So essentially one needs to formulate a sort of a evaluate like this, and in fact there are many software available on to calculate. In fact, if you just do this, this is the way that it should be provided, like 1 meter, 2 meters and all that, and spacing can be avoided, and design spacing, it should be 0.25, it should start here, and then with you can have spacing, and length is L is the length of reinforcement. So one should be able to design a suitable reinforcement layout, and there are many number of software that are available. They are company specific. They are also one can design systematically using an Excel program and all that. So essentially what we discussed so far is that yes, some sort of a design, if reinforced soil walls is possible using a given type of reinforcement, or you can even recommend a given type of recommend or check the stability of this reinforced walls, considering internal stability as well as external stability and all that. And with this, I'll conclude. Thank you.